Because addition is commutative and associative, the sum of a finite set of vectors is the same for all ways of adding them. The book's example is 3 vectors, which can be summed in 12 ways, all giving the same result. So writing down the index set makes the sum unambiguous. We can write the sum over I and I without saying how we got it. In general, any finite index set of vectors determines a unique sum vector. The index set is often a block of integers from 1 to n, and then the vectors form an n-tuple, added in their natural order unless directed otherwise. But unordered index sets come up often. The monomials of a general polynomial in 2 variables have no natural order. The book stars the formal proof and gives it only for the interested reader. It is an induction on the number of elements. The last addition in each computation splits the index set in 2. Intersecting the 2 splittings gives 4 pieces, and induction regroups them. With sums in hand, we can define a linear combination. A vector is a linear combination of a set A if it is a finite sum of scalars times vectors of A, where the scalars are arbitrary. For example, if A is the set of all powers, the linear combinations are exactly the polynomial functions. If A is sine, cosine, and the exponential in that listed order, then 3 sine minus the exponential has coefficient triple 3, 0, minus 1. Here is a concrete one. Take 2 vectors in 3 space. The set of all their linear combinations is plainly closed under addition and scaling, so it is a subspace. And any subspace containing the 2 vectors must contain all of their linear combinations. As a theorem, if A is a non-empty subset of a vector space, then the set of all linear combinations of vectors of A is a subspace, and it is the smallest subspace which includes A. The proof has 2 halves. Closure. Adding 2 linear combinations and collecting terms gives another, and scaling gives another by distributivity and induction. Smallest. The set contains each element of A, and any subspace, including A, must contain every linear combination. If A is infinite, we cannot list it in one go, but the argument still runs. 2 linear combinations are each finite sums, so their sum is again a finite sum of scalars times vectors of A, hence again a linear combination. This subspace is the linear span of A. If it is the whole space, A spans the space, and a space with a finite spanning set is finite-dimensional. Coordinate in space is spanned by the vectors with a single 1 and zeros elsewhere. Continuous functions on an interval are not.